In this video, we'll discuss the random effects ANOVA model, which is in direct contrast to what we've been talking about or assuming thus far, which is the fixed effects ANOVA. So the random effects ANOVA is in your textbook. You can check it out. It's section 3.9. And it comes into play when we have a large number of possible factor levels. So for example, consider well, there's many examples you could do, but let's say I want to look at the relationship between your favorite pizza topping and your IQ. So your IQ is the outcome, and your favorite pizza topping is the independent variable. Now, there's like pepperoni and sausage and bacon, which are, of course, the best pizza toppings, but you could also have other things like asparagus and I don't know, anchovies and like super weird stuff. So with that, in that particular case, there's a large number of different factor levels. And so when there's too large of a number of factor levels for us to include them all in our study, so let's say theoretically there's an infinite number. Another common example is if I'm trying to judge a performance. Well, if I want to study the judge effect, if I only have a couple judges who are just representing a randomly selected group of judges, well, then there's a large total number of judges I could select from, theoretically an infinite number of judges I could select from. And random effects are a way in which we can address this particular issue when we've got a very, very large number of factor levels that we can choose from. And so we're not reasonably going to be able to have all of the different factor levels. Like we can't reasonably have all the people in the world judge a contest. We can't reasonably study every different kind of pizza topping. So we're just going to have to pick a few. And when we have to pick a few, that's where random effects comes in. So what ends up happening is the experimenter chooses A, or again, capital I, depending on the notation, but the experimenter randomly chooses a number of these factor levels at random, and those are the ones that you're going to use in your study. Now, the trick here and the complication is that you really don't want to just make a decision about those A factor levels that you picked because you don't really care about those A factor levels. Your goal is to look at the whole group, the effect of the factor, which has way more factor levels than just those A you picked. So the goal is to be able to make inferences about all of the factor levels, even though you only have A of them. It's kind of like when we're looking at our data, we want to be able to make inferences about the whole population, not just the sample we got data from. It's the exact same concept here. We want to be able to make inferences not just about the number of factor levels we end up choosing, but we want to be able to make inferences about all of the factor levels, even those that we haven't gotten the chance to look at. So really the only difference between random and fixed effects is how the factor levels are selected. So in random effects, we randomly pick the factor levels. In fixed effects, either we care about them or they're selected for some other reason. We either care about them, so we select them for a reason, or we just use all possible factor levels. So one other thing to consider here is that when I say that the only difference between these is the factor levels, that includes the analysis. And we'll talk a little bit about the theory as to how that could possibly be true. But the analyses for these two are going to be the exact same. And so this is a really good thing. What changes is the interpretation. The interpretation changes, and it's because you didn't intentionally pick the factor levels. You randomly selected the factor levels. And when you do that in your design, so this is how your design changes your interpretation. The analysis doesn't change at all, but if you use the random effects ANOVA design, then in that particular case, it's going to impact your interpretation. So again, in fixed, we care about the individual levels. So we're either going to use all of the levels. So think about if I'm asking if you prefer Pepsi or Coke. Well, if that's my question, then the type of soda has two levels, Pepsi or Coke. I don't have to care about Mountain Dew. I don't care about Dr. Pepper. I'm only asking about Pepsi and Coke. So I'm using all of the population of levels that are being considered. Or I could take Pepsi and Coke as a purposive sample. This means that I take a sample intentionally. I have a good reason to select these two out of all the different levels of carbonated beverages you can select from. Note that the results here don't generalize to the population of levels. Why is that? Well, you didn't randomly sample from the population of levels. So I should be careful here and say the results of a purposive sample don't generalize to the population of levels. Of course, if you are looking at the population of levels, of course your results are representative of that full population. Now for the random effects ANOVA, again, we don't care about individual levels, so we're just taking random samples of the factor levels. The other thing here is that random effects ANOVA, we have too many factor levels to be included in our study, so we couldn't look at the whole population of levels. And because of this random sample of factor levels, that's what allows us to generalize to the population of levels. All right, so the model notation, again, I tend to use something slightly different, and fixed versus random effects is where these differences do come into play. So for fixed effects, what I tend to do is I tend to write, you'll note that the tau has changed to an alpha. So the textbook had a tau here, and that's what we looked at previously, but now I use an alpha. So I have the dependent variable is the grand mean plus the effect, the treatment effect. So it still means the same thing, it's just a different letter to mean the same thing, plus the error. And you'll see why it's a different letter in a second. And again, we have this distribution of the error. Now for the random effects model, it's going to look exactly the same, except alpha, the Greek letter, which stood for a fixed effect, is going to change to A, which is going to stand for a random effect. So A is going to be a randomly selected factor level from A sub I is representing the randomly selected factor level from all of the different possible factor levels we could have selected from. Now, be careful here or follow along closely. Alpha was selected intentionally. These are the specifically selected factor levels, or just the population of factor levels that we're selecting from. A is itself random. We randomly selected it. So because it's random, it has to have a distribution. So the effect of A is normal with a mean of 0 and a variance that's just kind of its own variance component. It's the variance of the factor level effects in the population of factor levels. So if I looked at all of the possible factor levels, this is the variance of those. And of course, the epsilon still has its traditional old variance definition. So keep these straight, sigma squared and sigma squared sub A. Sigma squared is the error variance. Sigma squared sub A is the variance of the treatment effects of all of the possible population of factor levels. Now I'll note again, because of this difference in notation, you'll see in the textbook this is called sigma squared sub tau, while we're going to call it sigma squared sub A. All right, so for some of the random effects model details, as we just saw, the model uses a random distribution for the factor effects. Now, because these factor level values, these factor effects, are assumed to be independent of the errors, the variance of the observation can actually be broken down. And I hope you're seeing a common pattern here where we take the variance of all the data, or we take some squares of all the data, or the degrees of freedom of all the data, and then we break it down into the different components, the component that has to do with our treatment effects, and the component that has to do with the error. And that can happen here because the variance that is associated with the treatment effects is independent of the error, or said another way, the treatment factor levels are independent of the error. So we can look at these variance components distinctly. Again, this is similar, though it's not exactly the same, to that fundamental ANOVA identity, where we take the total variance and we break it down. We take the total sum of squares and we break it down, the total degrees of freedom, and break it down. I hope you're seeing a common pattern. But now we're talking about variance components. And why are we talking about variance components as opposed to sum of squares? Well, they are very similar, but we're looking at variance because now we're looking at a population of levels that we can't study, a population of factor levels that is too large to be studied. So we're taking a random sample of the factor levels. So we are going to get some random variation in the factor effects that we see. The factor effects are going to be representative of the total variation of factor effects, but they're going to be a random sample of that. All right, so a covariance structure. And again, this all comes from the fact that our independent variable is now random. And what do I mean by that? Some students get confused. Please don't get confused here. What I mean is that I literally picked out of a hat, which is filled with all of the possible pizza toppings I ever could study, 3 different pizza toppings. And so I picked anchovies, peanut butter and jelly, and Pepsi. Those are 3 different pizza toppings. And so now I'm going to study those. And those are going to be my 3 factor levels. And again, I didn't intentionally pick common ones. I just took all of the possibilities, all of the reasonable possibilities, all the possibilities that are within my consideration, and I randomly picked some. So when I say my independent variable is now random, what I mean is I literally randomly selected those values. And as part of that, what that means is that the treatment effect, the effect of Pepsi being your favorite pizza topping on your IQ and the effect of peanut butter and jelly being your favorite pizza topping on your IQ, well, the effect of that particular treatment is random because I didn't know which ones I was going to pick. So the 3 different factor levels were randomly getting treatment effects because I was randomly picking which factor level would be selected. Now, because of this, we have to look at covariance in the data. So we're going to assume these below covariance structures. So the covariance between an observation and an observation within the same group is the within group variance for different observations. The covariance between an observation and an observation in a different group is 0. So we're assuming that if I have 2 data points and they're in different groups, then they're completely unrelated. And this is a very common assumption. But we're assuming that if I have 2 data points and they're in the same group, that they are going to be related. And this is a random component yet because until we select the factor levels, we really don't know how they're going to be related. So again, before the experiment, we expect the observations within the factor levels to have this random potential contribution which makes them similar. After we select the components and run the experiment, then we know which factor levels we selected, and this is no longer random. And that gives us our traditional assumption of independence. All right, the variance covariance matrix. So hopefully you've gotten a chance to see these in your math stats course. So we're going to do just a small test example to kind of demonstrate what's going on here. And we're just going to use a vector of y values of outcomes, which has 3 groups and 2 replications. So this is group 1, first observation, group 1, second observation, group 2, first observation, group 2, second observation, and group 3, first observation, group 3, second observation. So 6 total data points from 3 groups with 2 replications. And we're going to look at the covariance of this. Now, don't get too overwhelmed. So in a covariance matrix, if you've never seen one before, if you have seen one before, hopefully this is a good review. If you've never seen one before, what this looks at is for every row, 1, 2, 3, 4, 5, and 6, and every column, 1, 2, 3, 4, 5, 6, we have a row and column for each one of our data points. And so whenever the row and column meet, so let's say I go to row number 5 and column number 1, that says what's the relationship between data point 5, the third group, the first observation, and data point 1, the first group, the first observation. And what we said earlier was if you're in 2 different groups, you shouldn't be related at all. So that's why there's a big fat 0 there, is because they're in 2 different groups, so they shouldn't be related at all. The diagonal of a covariance matrix is the variance of the observation. So this is the variance. What are all the variance components? And we talked about in a previous slide that the variance of y can be broken down as the variance due to the factor effects and the variance due to the random error. So the variance of y is those 2 variance components combined. Now you'll see that there's a couple sigma squared sub a's hidden in all the zeros here. Now when does that happen? Well, that happens with data point 2 and data point 1. So data point 2, data point 1, data point 1, data point 2. That happens with data point 3 and data point 4, and that happens with data point 5 and data point 6. So why does it only happen with 1 and 2, but not 2 and 3? Why does it only happen with 3 and 4, but not 4 and 5? Why does it only happen with 5 and 6, but not 4 and 5? Well, if we look at what combines 1 and 2, but not 2 and 3, we see that 1 and 2 are actually in the same group. So what's going on here with these variance components is that if you're in the same group, you have a variance component that's connecting the observations in the group and making them similar in a way that they're not similar to data points in the other group. So that's what these components in the variance covariance matrix are representing, is the similarity within groups. And again, the randomness, which indicates that we don't know what that similarity is going to be. We don't know what that treatment effect is going to be until we select it. All right, testing with random effects. So with random effects, this fundamental ANOVA identity is still valid. However, the hypotheses change. So because we're talking about variance components, I no longer care about the mean. I don't care about the individual means. What I'm testing is, do the levels change? Does pizza topping as a whole have an effect? I don't really care about peanut butter and jelly as a pizza topping. That's not what I'm studying. I just randomly selected pizza topping. So I don't care what the mean IQ for pizza topping is, for peanut butter and jelly pizza topping is, because that was just one I picked out of a hat. That doesn't really matter to me. What I really care about is, does the factor as a whole have an effect? And that's why we're talking about these variance components instead of the means. So this affects our hypotheses. So the null hypothesis, instead of being written about all the means, now becomes written about this variance component. Is the variance of the factor effects 0? So think about what this means. If the factor effects don't vary at all, that means that if I pick a different pizza topping, it's not really different because it doesn't vary. If I pick another different pizza topping, it's not really different because it doesn't vary. Well, that means that they're all the same. Just think about that for a second. If I pick one and it's not different, and I pick another one and it's not different, that is, the results don't vary at all. Another way of saying that the results don't vary is that the results are all the same. So this null hypothesis is actually kind of the same as what our means was. It's saying that the effect of the different factor levels that I pick are not different from one another, or said another way, the variability in the factor effects is 0. There is no variability. They don't vary at all. They are all exactly the same. Now, because variances are always positive, the alternative hypothesis is that there is variation. So you either don't have variation or you do have variation, but you don't have negative variation. So in this particular case, our alternative hypothesis is always going to be written as a one-tailed hypothesis, that you do have variation among the factor effects. So either you don't, that's our null hypothesis, or you do have variation among factor effects. And again, what does this mean? This means that if I pick one, it could be different than a different one. They vary from one factor level to the other. And my random effects research question is all about, do the factor levels vary from one another? So because the random errors and the random factor levels are independent, this F statistic still holds true. So we have to rely on the fact that these random components are independent of one another, as we did in the previous slide. But because they're independent, we still get that same F statistic, that F is the mean squared treatment over mean squares error. Again, this is the exact same thing as we had previously, and we're going to demonstrate it in the next slide. So this is distributed as before. It's distributed as an F statistic with 1 minus alpha level, and then A and A times n minus 1 degrees of freedom for the numerator and denominator. Actually, this shouldn't be A, should it? This should be A minus 1. See, I've got all sorts of typos in these. I apologize about that. This should be 1 minus alpha. This should be A minus 1, comma, A times n minus 1. I apologize about that. All right, so let's go through the proof. The expected values of random effects. So what ends up happening here is this F statistic is built off of the expected values of the mean squared treatment and the mean squared error. So if the expected value of the mean squared treatment and the expected value of the mean squared error are both the same as what we had in the fixed effects case, then we feel confident that the random effects test is the same as the fixed effects test. So in the expected value of the mean squared treatment, we can break this down. 1 divided by the degrees of freedom times the expected value of the sums of squares, and then we just sub in the sums of squares. We're going to do a little distributing here, so we're breaking these components down into what they are, and then distributing some of the stuff out. And then what we're able to do is distribute the squared component into here, and we end up getting these different variance components in addition to the mean. And what you'll notice is that some of these components cancel. Some of these components give us this a minus 1 that's going to end up canceling with that fraction. And what we end up getting is the expected value of the mean squares treatment is the error variance, population error variance, plus the number of replications times the population level of factor effects, so the population factor effects variance. And again, you'll note in the textbook definition they use sigma squared sub t or sub tau, while I use sigma squared sub a. Now the expected value of the mean squared error similarly is going to be just sigma. So what ends up happening is that because these two are the same, the ratio is the exact same as what we're looking at earlier, and the ANOVA F test is identical to the fixed effects case. And this is really, really, really good news because that means we don't have to learn a new analysis when we're assessing a random effects model. We just have to ask when we're actually doing this practically, how did you pick the factor effects? And then change our interpretation depending on how you pick the factor effects. If you pick them purposively, or if you're using the population of levels, then your results are only going to apply to the levels you selected. If you pick them randomly from the full population of factor effects that you, or factor levels that you could have selected the factor levels from, then in that case, your results are going to apply to the full population of factor levels. It depends on how you designed the study, which should make sense. If you design a study differently, your interpretation changes. And it's pretty cool here to see how this same analysis can be used for two different study designs and for two different sets of conclusions, depending on what we're trying to get at inside of our study. Now, I should note that sometimes you'll see an ANOVA table that has expected value, and then you'll have this written next to in the treatments column and this written in the error column. So that is something that you can add on. You just add on another column for expected value. Another thing I should note here is that the results here are true when there is only one factor, but we have to be a little bit more cautious when there are more than one variable. And it's because the expectations hold are a little bit different, and the breakdown is actually, well, of course, more complicated. The other thing is that this type of a proof actually holds for the fixed effects. So normally we don't worry about doing this in a fixed effects case because we're not looking at the variance components of the factor levels, because the factor levels aren't varied. There is no variance component of the factor level from the population. That is our observed value. But it does hold. We just usually don't do this breakdown for the fixed effects.